In the previous lecture we were discussing about the statement of first law of thermodynamics for a cyclic process undergone by a control mass system and for any general process undergone by a control mass system. Now in the process we learnt about a property called as internal energy. So we will learn one more property, and that one more property we will learn through a particular example. So let us take an example of a constant pressure quasi equilibrium process. So this is a very common example encountered in thermodynamics. Where you have say a piston cylinder arrangement, there is a system here and this piston moves maybe because of heat transfer to the system Q12. The piston moves slowly so that the pressure inside remains the same. Why? If it moves slowly, the pressure inside will remain the same, the resistance pressure also remains the same. The resistance pressure is nothing but the atmospheric pressure plus the pressure equivalent pressure due to the load of the piston. Because the resistance pressure does not change, so the inside pressure also will not change if this is moving in a quasi equilibrium process. So that kind of process we are considering. So let us write the first law for the system. So it is basically the integration of delta Q is equal to dE plus delta W, you integrate it from 1 to 2. So this we call as Q12, not Q2 minus Q1, because this is not a property, this is the total heat transfer during the process 1 to 2. But this is the difference in property E2 minus E1 plus W12. So if you neglect changes in kinetic energy and potential energy, then E2 minus E1 is as good as U2 minus U1. So Q12 this is, let us say that the system is a simple compressible substance. So if it is a simple compressible substance, then the work done due to this moving boundary is integral PdV from 1 to 2. So constant pressure quasi equilibrium process, let us qualify this a little bit by saying that of a simple compressible substance. Otherwise PdV may not be the only form of work, there may be other forms of work as well. So, the PdV in this case, because pressure is a constant, this is as good as P into V2 minus V1, and because P1 and P2 are the same, this is as good as P2 V2 minus P1 V1. So, you can write Q12 is equal to U2 plus P2 V2, we can combine these together, minus U1 plus P1 V1. So, this U plus PV is a property. Why? U is a property, P is a property, V is a property. Therefore, their combination is also a property, and that property U plus PV, this is defined as enthalpy. So, enthalpy is defined as a property. Although we have introduced it through this example, never get confused by thinking that it is valid only for a constant pressure quasi equilibrium process, not like that. This is an example where the heat transfer comes directly as a difference of enthalpy. This is a consequence of the first law of thermodynamics, but enthalpy is a property which is valid at any state point, because any state point will have a pressure, volume and internal energy. Therefore, their combination will exist for any state point, no matter what kind of process that has taken place to arrive at that state point. So, this will become H2 minus H1. Okay. So, with this background, we have come across two properties, and these two properties, internal energy and enthalpy, they are tabulated in property tables. Sometimes internal energy is not separately tabulated, but if enthalpy and pressure and volume are tabulated, you can calculate internal energy by H equal to U plus PV. So, U equal to H minus PV. So, just like specific internal energy, specific enthalpy H is capital H by M. So, this is U by M plus PV by M. So, this is small u plus P into small v. So, in the table it may not be that H and U are both given, maybe one of them is given, but you can calculate it from the other if pressure and specific volume are known. The next set of properties which we will learn in the context of first law, not that they are directly outcomes of first law as such, that is the specific heats of substances. Okay. So, now when we say specific heats of substances, we will start with an example, a very abstract algebraic example, and we will bring out the physics as we go along with the example. So, let us consider internal energy as a property. So, how do you estimate a property? You estimate a property when you identify the state point, because the property is a unique function of the state point. The state point can be ascertained if you specify two independent intensive thermodynamic properties for a simple compressible pure substance. This is called as a state postulate. So, state postulate means that how do you specify the state of a system, thermodynamic system. For a simple compressible pure substance, you require two independent intensive properties. So, in this case, let us take temperature and specific volume as two independent properties. You could also take temperature and pressure, or if they are at all independent, but in this case just for convenience let us take any two. So, these two is good enough, because these two if they are independent they will specify the state, and then u is a unique function of the state. So, that is the meaning of this functional dependence. So, when you write this u as a function of t and v, so you can write du, which we will write as a partial combination of partial derivatives okay. So, the total differential is sum of the partial differentials, that is what, this is the basic rule of differential calculus. We have not brought any physics here except for writing this as a function of two independent thermodynamic properties. So, then we just give a definition, this we define as CV, specific heat at constant volume, and why do we call this as specific heat at constant volume will be very clear if we do a few additional steps. But the definition is not governed by the physics, the definition is governed by this simple mathematical expression, and this simple mathematical expression is a property. Why it is a property? Because it is a partial derivative of one property with respect to another property, given another property remaining fixed. So, that is also a property. So, this CV is called as specific heat at constant volume. Question is why? So, let us imagine a constant volume process, although see CV is defined for all processes. The way in which it is calculated is that u is varied with t given v as constant, but once this property is evaluated, because it is a property, this property does not depend on a process. So, that means that if you have a state point where you have a temperature and specific volume, at that state point you have a unique CV. So, how that state point is arrived, whether it is arrived at a constant volume process or not is not important, this physical sense you have to develop. Although the property is defined in this way, it is just for the sake of evaluation of the property, but once the property is evaluated this can be applied to any process, right. It is not just restricted to constant volume process. But imagine why it is called as specific heat at constant volume. Imagine a constant volume process. If you imagine a constant volume process, then dV is 0, right. So, then du is Cv dt. So, in that case if you apply the first law with negligible changes in kinetic energy and potential energy, you have this one, right. See, I will not specify the assumption again and again, but for a few times I have already iterated, because some of the students take this as granted, you know, but you have to keep this in mind that this is not granted, provided this is true only if there is negligible change in kinetic and potential energy. That must be remembered, although every time we may not write it explicitly or tell it explicitly, but whenever we are writing this, it means that kinetic and potential energy changes are negligible. So, now for a constant volume process there is no work done, right. So, this du, so it is del q for constant volume process is Cv, this is mass, this is capital U. So, this is mass into small u. So, mass into Cv into change in small u is this one. So, you can also write Cv is 1 by m this one, right. So, recall the school level definition of specific heat. The heat required to increase the unit mass of a substance by a unit temperature. Here it is also like that, it is this del q, it is what? So, Cv is what? The heat required to increase, if m is equal to 1 and this is equal to 1, then Cv is the heat transfer. That means the heat transfer required to increase the unit mass of substance temperature by unity, given that V is kept constant during the heat transfer process. So, that is why it is called as specific heat at constant volume, that is the physical meaning, but keeping this physical meaning abstract, you can come with this definition of Cv without relating it to this. Similarly, so this is called as specific heat at constant volume. Next we will learn the definition of specific heat at constant pressure. So, let us take an example. Say enthalpy as a property. So, just as we wrote u as a function of t and v, we can write h also as a function of t and v, but here for our purpose of defining the property that we want, we take h as a function of t and p, assuming t and p are independent. For example, you cannot write h as a function of t and p when the substance is changing its phase, because when the substance is changing its phase, t and p are dependent on each other. The saturation pressure is a function of saturation temperature. So, they are no more independent parameters. Okay. But in case they are independent, you can write this. So, then dH this is what we write exactly in the same way as we wrote for du. This we define at Cp, specific heat at constant pressure. Again, why such a name? Let us consider, imagine a constant pressure quasi equilibrium process, the example with which we started this lecture. So, if you imagine a constant pressure quasi equilibrium process, again for defining this property such a process may not be necessary, but this is to give a physical interpretation to the property. So, we have just seen that in that case the heat transfer is the change in enthalpy, the first example that we did today. So, then in place of this, so because it is a constant pressure process, in that case dH is Cp dt. So, this is m Cp dt, because for constant pressure process this is 0. So, you can write Cp is 1 by m okay. So, this gives a physical interpretation to Cp, that it is the heat transfer required by unit mass of a substance for unit change in temperature, given that the heat transfer is taking place at constant pressure. That is the physical interpretation to Cp, just analogous to Cv. Now, without getting into any mathematical argument, of course by mathematical argument we can show this, it is we can make these observations. First observation is Cp greater than Cv. So, why it is so? See, physically when you are supplying heat at constant pressure, you also keep a provision of change in volume, and that equivalent energy must be supplied to achieve that change in volume. Whereas, when you are supplying heat at constant volume, you do not need to keep a provision of any heat energy transfer to accommodate change in volume. So, this under identical changes of temperature, this will require a constant pressure process will require a more greater supply of heat, and that means Cp is greater than Cv. Then imagine the molecular origin of this Cp, Cv and all this. So, these are all associated with certain derivatives, temperature derivatives of internal energy. So, that means they are intrinsically associated with intermolecular forms of energy. They are the translational modes, the vibrational modes, the rotational modes, all the modes of the molecular motion. So, now when we think of monoatomic gases as an example, so let us think of gases. For monoatomic gases, you have the translational modes only, right. So, other modes are not relevant, like vibrational, rotational, these modes are not important. So, what are these monoatomic gases like helium, argon, monoatomic hydrogen, like this. So, if you have nascent hydrogen for example. So, but typically we say these types of gases, because hydrogen will normally be there in H2 form rather than H form. So, if you have these gases, so they do not have these modes of energy beyond the translational. So, for them Cp or Cv are virtually independent of temperature, because they will remain constant over a wide range of temperature without being dictated by the changes in the vibrational modes of kinetic, the vibrational modes of energy with changes in temperature. Now, if you have diatomic gases, those modes will be there. So, for diatomic gases, those modes are there, but the dependence of CpCv with temperature is not that high as that for polyatomic gases. So, if you have more and more number of atoms added in a molecule, you will have the more severe dependence on Cp and Cv with temperature. So, CpCv depends on temperature, but not severely. So, diatomic gases like H2, O2, these kinds of things, N2. Polyatomic gases like CO2 for example, there CpCv dependence on temperature is much more severe. So, when we talk about CpCv dependence on temperature, we must keep in mind that why we are bothered so much about CpCv dependence of temperature. We are bothered so much about this because for gases, of course, CpCv will depend on temperature and pressure or specific volume, but the dependence on temperature is primary. In fact, it is shown, it can be shown that for ideal gases CpCv depend on temperature only. So, this is the third point. For ideal gas, Cp and Cv are functions of temperature only. So, in fact, this can be mathematically shown, but in 1843 Joule did a very classical experiment. So, what he did is, I am briefly explaining the experiment. There is a water bath in which these two bulbs were connected, this is water and here it is air and here it is vacuum. So, there is a stopcock here which prevents these two from mixing and there is a hot water bath here. So, he kept a thermometer inserted to measure the temperature, and when this stopcock was opened, this air occupied the entire volume. In this process there was no work done because it was a free expansion. So, the entire heat transfer was due to the change in internal energy. So, if you write for example, if the work is 0, then the heat transfer is this. So, now if this system is insulated, then this del Q is also 0 and then there is no change in internal energy, and Joule measured that the temperature also remained the same. So, the internal energy for in this case where air was approximated as an ideal gas was supposed to be only a function of temperature. Of course, this is not a proof, but rigorously through thermodynamic property relationships it can be shown that for ideal gases internal energy is a function of temperature only. So, then you can write du. So, Cv for ideal gas, for ideal gas we give this 0 as a subscript, this is simply du dt, right, because u is a function of t only. Because u is a function of t only, its derivative is also a function of t only, therefore Cv is a function of t only. Similarly, Cp is dH dt. Interestingly, Cp minus Cv for an ideal gas, 0 for ideal gas, is ddt of H minus u. H minus u is Pv, and for ideal gas Pv equal to RT. So, this shows that Cp minus Cv is equal to R for an ideal gas. Finally, I would like to conclude with a very important definition which is called as perfect gas. There is a difference between ideal gas and perfect gas. For ideal gas, Cp/Cv is a function of temperature, but for perfect gas or calorically perfect gas, the Cp/Cv is considered to be a constant. So, that temperature dependence is no more considered to be important. So, for an ideal gas, Cp and Cv are functions of temperature only. For perfect gas or calorically perfect gas, those are special cases of ideal gas where Cp, Cv are constants. So, calorically perfect gas Cp, Cv constants. And finally, for incompressible substance, see this specific volume at specific heat at constant pressure or constant volume, this distinction gets lost when it is an incompressible substance. Constant volume, constant pressure, all these things do not matter. So, in that case you can write Cp is equal to Cv equal to C. Okay. So, this is a unique specific heat where the distinction between Cp and Cv is completely lost. Cp is equal to Cv equal to C. So, with this little bit of background on the specific heats, we stop here today and we will continue with some problems in the next lecture. Thank you.